Hello my dear students. Today we are in very important lecture. Today we will start chapter number 6 of NCERT. It is electromagnetic induction. I am B S Pandey. My dear students, let me start today's lecture. It is lecture number 64. And today we have entered in chapter number 6 of NCERT. It is electromagnetic induction. Chapter number 6, electromagnetic induction. EMI. My dear students, actually the electromagnetic induction, it is the word electromagnetic induction. Magnetic induction, it is very clear with its name. It is electro and magnetic. Yani, I mean, using magnetic field, we will induce electricity in this chapter. Induction of electricity using magnetic field or the magnetic field lines, that is the flux. Okay, my dear students, if we will try to give the definition of this particular topic, that is electromagnetic induction, it will be inducing EMF or the electric current in a coil due to change in magnetic flux is called electromagnetic induction. Okay, my dear students. So to study the electromagnetic induction chapter, there will be the number of topics we will study. We will start with the magnetic flux, and then we will study how this magnetic flux linked with a coil changes, which causes induce an EMF, and due to resistance of the coil and current can be induced and can be studied. We will also study how the electric field or the charge induced can be studied through a coil in this chapter. Then we will study if current is induced. If a current is induced in a coil, then what will be the direction of current, whether it is clockwise or anti-clockwise, and that will study with the help of Lenz's law. Okay, my dear student. So let's start with the magnetic flux, this chapter. Magnetic flux. We'll represent this magnetic flux by phi B. We have used the symbol phi for the electric flux also. So here we have given here a subscript B to distinguish this magnetic flux, and we can use phi E for the electric flux over there. What is this magnetic flux? Actually, this magnetic flux is nothing but the counting, as we have studied the electric flux. It is the counting of field lines crossing a particular area. Suppose, my dear students, we are having a magnet. Suppose this is the North Pole, and here we are having a plate, okay, a sheet. Here the field lines is living. You can see I may change the dimension to understand well. Here the magnetic field lines are moving towards the plate, and if you will try to count the number of field lines in encounter with this plate, you can say here 1, 2, 3, 4, 5 lines are encounter with the plate. It means this plate is counting how many field lines. It is total 5 field lines counting by this plate. So we can write here the flux, it is nothing but the 5. Remember, it is the counting of field lines by any cross-sectional area or by any surface. This is the magnetic flux, nothing else. So this magnetic flux is the counting of field lines. If we'll try to give the definition of this magnetic flux, then you can say it is the total field lines crossing through a particular surface area. It is known as the magnetic flux. Okay, my dear students. Here, What will happen if we'll tilt, this is the plate, if we'll tilt this plate at certain angle, here the cross-sectional area of this, or the area of the plate, you can say in this direction. Okay, what will happen if you will tilt this plate? Of course, the field lines encounter with the plate will decrease like this way. If you will tilt the plate, now the field lines, it is going, you can see here the total field lines encounter with the plate, now it is only 3. Now the flux is 3. Okay, so as you are tilting this plate, what will happen if you will tilt the plate and it will be perfectly horizontal. This is the field lines. All the field lines, it will be go either above the plates or below the plates. But this plate in this case is not able to stop any field lines, and it will not count any field lines striking because its thickness is very small. So we can say here the flux is almost 0. Alright, so by changing the area, here the area, if you would like to see, area will be in this direction. Here it is area in this direction. We have rotated at certain angle, and here it becomes 90 degree. So you can see here the flux is changing in this way. In each case the area is same, but the counting of field lines in each case it is changing. Okay, and this counting of field lines is termed as the electric flux. Okay, my dear students, this is the definition of the magnetic flux. It is the magnetic flux. My dear students, you can give the mathematical definition of this magnetic flux also using this particular diagram. Kindly keep this diagram in your mind. I'm going to explain it. Suppose we are having a coil and through which magnetic flux linked like this one. This is the magnetic field lines. Magnetic field lines. Now the coil is tilted by some angle. Suppose it is rotated at certain angle. Its coil area is the direction of magnetic field, but this area of the coil, it is rotated at certain angle. Suppose it is A. Okay, it is theta. In which direction we will get the maximum flux? That is the maximum field lines encountered by this plate. Of course, we have a study right now. If the plate will be in this direction, it will encounter maximum field lines as it can encounter. But as you will rotate the plate, the field lines will decrease. It means if the area will be in this direction, okay, if area it will be in this direction, the maximum flux can be studied. We are going to give here the definition for the maximum flux. So this A can be taken as the component along the magnetic field. It is A cos theta. It means magnetic flux will be defined for this area. Which one? A cos theta. And it is the mathematical product. Remember, this flux, magnetic flux, it is defined as the product of magnetic field and area vector. So this can be written as the magnetic field and area vector. It is A cos theta. So you can write here using concept of vector. B is magnetic field, which is the vector quantity, and this is also vector quantity. So B dot A we can write. This is not very tough, my dear students. We have studied the electric flux also. Here the magnetic flux we are studying. It is B dot A. This is the area and the magnetic field. So it is the dot product of magnetic field and area vector. Here we have studied about the magnetic flux. This unit of this magnetic flux is considered as the Weber. As a unit will be considered as the Weber. That's why the magnetic field also having a SI unit, it is Weber per meter square. But the magnetic flux, for the magnetic flux, we will use the SI unit as Weber. Okay, my dear sir. So this is the magnetic flux. I hope you understand about the magnetic flux. Now, we proceed for the next topic, and it is the experiment. It is the experiment done by the Faraday in his course. We have to study. Okay. So my dear student, the experiment will write Faraday's experiment. Faraday's experiment. It is mentioned 4 experiment in your NCERT book 6.1, 2, 3 and 6.4. You can see. So one by one we will study all the experiments. Before starting the experiment, let me tell you the one thing about the electric flux and how this experiment will be studied. Look at here. This is the coil. You can also make this coil using a conductor by giving number of turns. Okay. So this is a very simple coil. Suppose we are given the number of turns to this coil. We are having the two end of the coil. We connected the two end with a LED bulb, which require very small amount of current to glue. This is the coil. This is the axis of the coil. A magnet is kept over here. Okay, a bar magnet is kept. Now, here the magnetic field lines is coming and linked with the coil. You can see this is not very tough to understand. This magnetic field lines are linked with the coil. You can keep this bar magnet north pole near the coil or south pole near the coil. There will be no effect on the magnitude of current we are going to study, or the EMF. Now, suppose this magnet is at rest. This magnet is at rest. So according to Faraday, he has done the experiment, and what he observed, if this coil is in a static state, this magnet and this coil, the relative velocity, remember this is the V relative, this V is the V relative. The relative velocity is 0. It means neither this magnet nor this coil is moving. Then in this case, there will be no observation on the bulb. Actually, we will see later on this bulb will glow. Okay, but here in this case, you can see the field lines is linked with the coil, but this field lines is not changing, it is constant. Suppose the 5 field lines is linked with the coil and it remains 5 field lines because this is stopped. Okay, what will happen, my dear students? Suppose if we will move this magnet towards the coil, here the number of field lines, it is moving out from the north pole. What will happen? If you will move this magnet towards the coil, the number of field lines linked with the coil will increase. And if you will get away this magnet, what will happen? The number of field lines linked with the coil, it will decrease. However, here the magnetic field lines is changing as you are moving this magnet with respect to the coil. The number of field lines enclosed with the coil, it is changing. Due to change in this magnetic flux, there will be EMF induced in the coil, and this was observed by the Faraday. And EMF will induce. In short, try to understand here. I am telling you, whenever there will be change in flux in any coil, there will be EMF induced, and due to resistance of the coil, there will be current induced in the coil. Okay, so you can write down till here. Now, one by one, we'll do the experiment. So the first experiment, you will give the heading experiment 1. Okay. Here, we are going to give a relative velocity to this magnet. V relative. Okay. This magnet moves in this way. As soon as this magnet moves, and till it moves, this bulb glows. Alright? Yes, this bulb glows, and this glow so that there is induced EMF in the coil and a current induced. Here E induced, or you can say I induced in the coil. This bulb glow. Remember, my dear students, there is change in flux takes place, and due to change in flux this bulb glows. This is the Faraday experiment. You have to understand this experiment carefully, because on the basis of this experiment, my dear students, we will study the law which was given by the Faraday. That will be very helpful to solve the numerical question. Okay, now the next experiment. In next experiment, what we have done, actually the Faraday did experiment number 2. Experiment number 2. In this experiment, Faraday just remove this magnet and place another coil. Behalf of this magnet, the n number of turns. But this coil is already connected with a source of potential, that is the voltage, and current is flowing. We know, my dear students, a current carrying coil behaves as magnet. So at the place of that magnet, we have placed here a coil, current carrying coil. Now, as the current is moving, the magnetic field will be induced, magnetic field will be generated by this coil, and this magnetic field will be linked with the coil again. Now, as you will move this coil, you will give V relative. What will happen? Again, this bulb will glow. This is the second experiment. You can see this is the same experiment. There is nothing much change in this experiment, my dear students. This bulb glows. Why? It is due to the E induced and I induce in the coil. Okay, my dear students, here the I induce and current induced due to the resistance in the coil. Now, the third experiment. Remember, my dear students, for this experiment, you can write in your notes one by one, 2 or 3 lines, so that in future you can understand what you have been written in your notes. Okay, now in third experiment, experiment number 3, a coil, LED connected. At the axis of this coil, we have placed another coil, given M turns. Now this battery is connected, but a switch is also given. Okay, here I am giving the switch key. Okay, it is the key, and this is the battery, plus or minus. This is the axis of the coil. This is the coil 1, this is the coil 2. Now, of course, both the coil is in rest. Now, of course, if you will not move, you have not tapped on this key, the current will be 0, and due to current 0, there will be no field induced. Can this bulb, could you imagine this bulb will glow if it is switched off? No. As soon as you will switch on, the flux will be linked with the coil. Okay, flux will be linked with the coil. But what will happen? If you switched on continuously, the field is linked with the coil, that is the magnetic field lines linked with the coil. What will happen? The field lines is constant, the field line is constant and there will be no change in field lines, so there will be no glow of this bulb because the field lines is not changing. My dear students, without changing flux, you cannot induce any current. So there will be no current. But as soon as you will switch off, what will happen? The field lines will goes off and the flux will be zero. Continuing switching on off, there will be change in flux to maximum and minimum, that is maximum to the zero. And due to change in flux discontinuously from maximum to minimum, that is the field line, the flux linked with this coil, the bulb will glow. So this is the third way to induce EMF in this coil. I induce and E induce. Okay, my dear students. Now, suppose if we do the fourth experiment, which was done by the Faraday, it is we are having a coil and that coil can rotate. Okay, that coil can rotate. If you allow the coil to rotate here on the axis of this coil, and this coil is going to rotate in this direction. Remember, a current is induced through this coil. So this coil having the magnetic field lines in this way. Okay, this coil is going to rotate in this way. The no flux linked with the coil, the field lines is going up and down. As it will rotate in this way, the field lines will link. As it will goes in this way, the field lines again in this way, and there will be no flux. As soon as this will rotate, what will happen? The flux will change through this coil, which is linked to the maximum and minimum. Again, this bulb will glow, which show the induced EMF. So this was the fourth experiment which was done by the Faraday, my dear students. And using this particular experiment, Faraday given some laws of electromagnetic induction. So my dear students, let's have a look over a clip, that is the video clip I got from internet. I'm sharing here to just make your concept more crystal. Okay, so let's have a look over this.
We're going to have a look at Faraday's law of induction. For this demonstration, we've got a ring which consists of many turns of copper wire. Regrettably, it's covered with tape, so they're not visible. It was known that when electricity went around a conductor, it produced magnetism. People had made electromagnets before Michael Faraday came along. If the magnet sits stationary inside the coil of wire, no electricity is made, and we can see that the meter needle is not moving. If the magnet is moved, the magnetic field within the coil of wire changes. And it is this changing magnetism that induces electricity. This is what Michael Faraday discovered. And notice that by moving the magnet in different directions, we produce electricity in either the forward or the backward direction. We can illustrate this with a bar magnet. The magnetic field of a bar magnet points away from the North Pole. And so we could imagine a series of magnetic lines coming from the north end with arrowheads pointing away from the North Pole and toward the South Pole. If I move that magnet into this conducting coil, I am increasing the number of magnetic lines that point in the direction I'm moving. So this is the reason that when I move a magnet in and out of an electric coil, I see my meter change directions and show me electricity moving first in one direction and then in the other. Another way to look at Faraday's law would be to produce electricity by induction and then use it. And so we've got an apparatus in which we have two coils, each of them placed vertically on the table. and above each coil is a magnet hanging from a spring. The magnets and springs are identical. If I move one of those magnets in and out of the coil, it will induce electricity. Second, we'll take a small battery and connect it to the second coil and see that when we put electricity into the coil, it produces a magnetic effect on the hanging magnet, and the hanging magnet moves vertically. So now we'll connect the two coils with wires and start bouncing the first magnet so it moves up and down at its natural frequency, producing electricity at that frequency. So the motion of the first magnet will be translated to the second magnet electrically, and we'll see the second magnet begin to move at the same rate as the first magnet because we are inducing electricity in the coil. The magnet doesn't just sit there, the magnet has to move.
Now, on the basis of that video clip, my dear students, we are going to write here law of electromagnetic induction, which was given by Faraday. So kindly give the heading first law of electromagnetic induction. The first law, you can give here Faraday law of electromagnetic induction. All right. So the first law. My dear students, as we have seen the experiment and we can conclude the EMF was inducing till the time the flux is changing. If there is no change in flux, there will be no EMF induced and current induced in the coil. So my dear students, we can write the first law, kindly write down, whenever magnetic flux linked with the coil changes, whenever magnetic flux linked with the coil changes, an EMF and hence current induced in the coil. This EMF induced lasts as long as magnetic flux changes. Full stop. This is your first law. What does it mean by the first law? According to this first law, the EMF will induce and it will last as long as the flux will change. The linked flux will change. Will stop the change in magnetic flux, EMF induced will be 0 and the current will be 0. Remember, the EMF induced will not remain constant. It is 0 and the current will be also 0. Alright. Now the second law. Second law, my dear students, write down the second law. The magnitude of induced EMF, the magnitude of induced EMF the magnitude of induced EMF must be directly proportional to the rate of change of magnetic flux. Full stop. What does it mean by the second law? It is directly proportional and a proportionality constant E, it is 1. So it can be written as d phi by dt. Magnetic flux we are talking about. So here the phi b, and here a negative sign was taken by the Faraday. We will study this meaning, the meaning of this negative sign also, but this was well explained by the Lenz in the Lenz law. But this negative sign, what it shows, we will study. My dear students, if there are n number of turns, if n is the number of turns in the coil, then we can write this magnitude of induced EMF, it is minus n times d phi by dt. This one is a very important. Okay, this is for n turns. Of course, if this n is 1, then it will be the minus d phi by dt. Now you can write about this negative sign. Negative sign shows that induced EMF, this induced EMF opposes, remember how it will oppose? So EMF induced in the coil actually will result to the electric current in the coil, and if the current induced in the coil, then that current will also produce some magnetic field. Of course, it is produced by magnetic field, that is the change in magnetic flux. But if the current induced in this coil, then this current will also induce a magnetic field. Exactly. So this negative sign we will study. The negative sign shows that in E induced opposes the change in magnetic flux. What does it mean? The EMF induced actually opposes the cause that has been induced it, and this is the Lenz's law. This EMF induced actually opposes the cause. What is the cause? Change in flux, and it opposes the cause that has been induced it. This is the Lenz's law. My dear students, we will wind up today's lecture with a very simple numerical question, and then we will start next lecture with fantastic explanation of the Lenz's law. Alright? So a very simple question, my dear students, here for you. Remember this law, it is E induced is equals to minus d phi by dt, and for n turns it is n times d phi by dt. Now the question, if flux linked with the coil is given, which is the function of time, it is at b naught, a constant t q. Alright, then find E induced as a function of time. E induced as a function of time, and R is the resistance. Then also find I induced in the coil. If you can solve, my dear student, this is very simple mathematics, then you can solve. Let me solve this question. Okay, here we know that E induced is nothing but the d phi by dt minus d phi by dt. So the E induced, it is minus d phi, it is given b naught tq by dt. As I told you, this b naught is a constant, so it is b naught d tq over dt minus b naught 3t square, and it is the function of time. You can see this is the answer. Now if R is the resistance, we know that according to Ohm's law, E is equals to I times R. So this I will be E over R, and it is minus 3 b naught t square by R. Remember, this negative sign has no significance. It is only giving the direction. So you can write here 3, the mod of this one, my dear students, ampere. This is the answer. Okay. So my dear students, we are concluding today's lecture. In next lecture, we will study about the Lenz's law and a few very important questions that you have to face in your board examination. Okay, my dear sir, thank you very much for today's lecture.